All right, I guess the dimming lights means it's time to get started. Hopefully you're all still awake on the last day of the conference. So welcome to Secure Pods, Sandboxing Workloads in Kubernetes. My name is Tim Allclair. I'm a software engineer at Google. I work on the Kubernetes engine team, doing various security things. I'm also co-chair of sig-auth and a member of the Kubernetes Product Security Team. So when I first submitted this CFP, the only time I did, it was the last day the CFPs were due, and we had just started to dig into secure pods. We knew we wanted to build on a lot of the great work that was coming out of the Kata container and Fracti and Cryo communities around kind of building these sandboxes, sandboxed runtimes. We knew we wanted to kind of integrate that deeper into Kubernetes and formalize the concept of a secure pod. But we didn't really know exactly what a secure pod was. So 5 months later, I'm here. We have a much better idea of what secure pod means. And now we're calling them sandbox pods to disambiguate. But the title of the talk is still secure pods. So let's run with that for a minute and talk about what a secure pod is. For people just getting here, there's still some seats up front. So for the purposes of this talk, let's consider secure to be synonymous with isolation. A little bit of a simplification, but makes it easier to talk about. And so when we're talking about isolation, we need to think of isolation as directional. So just because A is isolated from B doesn't necessarily mean that B is isolated from A. So in the context of pods in Kubernetes, we can talk about threats from the outside. So threats from the internet, big scary place, and all the attackers that want to get at whatever is running in our pods, in our cluster. And this is a really big, rich topic area, a lot of different things to help prevent attackers from the outside getting into our cluster. But this isn't what I'm going to focus on today. Instead, I want to talk about threats from the inside. So threats from within your pods and what we can do about that. But before we do, let's talk about why. Who put the cat in the cage? Like, who put the attackers in your pods in the first place? Why do we care about this? The first reason to care is if you're running untrusted code. If you are running a multi-tenant SaaS, for instance, where your users submit binaries or they submit container images or anything like that, you can't trust the code. You don't know what your users are giving you. Maybe you're running a third-party service. Maybe it's open source code that you just haven't fully security audited. You don't know exactly what's happening in there, and you want to have a little extra safety. The second reason is containment. Maybe you started with thinking about threats from the outside, and but the attacker penetrated your defenses. Now they're inside. You want to prevent lateral movement. You want to prevent them from getting at maybe the more sensitive parts of your service and getting deeper into your cluster. So what can we do about this? How do we deal with internal threats? It's actually much harder, I think, to deal with these internal threats. There's much larger attack surfaces. Not only do we have to worry about some of these same external attacks, but we also have to worry about attacks on the kernel, the syscall interface that's exposed to containers. We have to worry about the various storage interfaces. I can't remember how many we're up to, something like 20 or 30 different volume types in Kubernetes, and now we have CSI, and we'll have many more volume types that come with that. What happens if there's a vulnerability in one of those, the clients in your Fuse file system, for instance? We have the whole internal network, all the services and various things that are exposed within the Kubernetes cluster that might not be exposed to the outside. There's the daemons that provide different services to your cluster, and then we'll touch on hardware as well in the wake of Spectre and Meltdown. But let's start with the kernel. I'm sure you've all heard the term container escape. This is most commonly talked about in the context of the kernel, I think, looking at attacks via syscalls. And there's actually a lot of nice things we can do about this. Oh wait, I was supposed to say, let me engage in a little bit of good old-fashioned fear-mongering. In 2017, there were 169 code execution CVEs published in the Linux kernel. The good news is most of these are in drivers that are primarily used in mobile devices. So keep your phones up to date, but unless you're running Kubernetes on your phone, I bet there's at least one person at this conference doing that. You don't need to worry about this. And we actually have a lot of good tools to deal with the kernel attack surface today. Seccomp is a way of filtering out syscalls and reducing the attack surface. Docker has some really nice default seccomp profile that we turn off in Kubernetes by default. So you probably want to turn it back on. And this is the annotation that you can use to do that. We're trying to make that the default, but security defaults are hard. AppArmor is another tool. SE Linux is sort of the counterpart if you're running a SE Linux system. This is for defending sensitive files mostly. And this we do run by default. So you don't necessarily need this annotation. Hopefully you all caught Liz's keynote this morning and know that you should not run as root in your containers. This is labeled an advanced talk, so I won't go into this too deeply. But you also want to enable this allow privilege escalation, especially if your users are giving you untrusted containers, because otherwise you can trivially get to root by just running a setuid binary, and this prevents that. But what happens when these features aren't enough? Dirty cow I've already heard mentioned a few times at this conference. This was a vulnerability that came out 2 years ago. It's a race condition in the copy on write memory handling of the Linux kernel. And there's a cool proof of concept escape demonstrated via the virtual dynamically shared object that is injected into every process in Linux. And I'll link to that at the end. So now I want to introduce sandboxes. At Google, we have this principle, security principle, that between any untrusted code and user data, there have to be at least 2 distinct security boundaries. So that means 2 independent security mechanisms need to fail in order for that untrusted code to get at that user data. In the context of the kernel attack surface, since the kernel is a single kind of thing in memory, we basically need a separate kernel for the sandbox pod. Otherwise, a single bug in the kernel, like dirty cow, could lead to an escape from the sandbox. And that 2 security boundaries is an important concept, and we're going to come back to that throughout the talk. So one implementation of sandboxes is Kata containers. There have been a couple of talks, maybe you've been to them at the conference. It was announced in December, Kubecon North America, and it's a combination of Hyper's Run V technology and Intel's Clear containers coming together to make lightweight VMs that run containers. In the context of Kubernetes, we run the VM as the kind of the pod construct, and then we run containers within that. I'm not going to go too deeply into the architecture here, but we have a separate guest kernel, yeah. Maybe you heard the announcement about gVisor 2 days ago. This is a new open source project from Google, and this is actually the sandbox that we use at Google in a lot of places in the production environment. This is a little different from a traditional VM. You have an emulated kernel. It's basically something that implements the Linux syscall interface running in user space. And then this platform thing that just bounces syscalls into the emulated kernel. And I just wanted to highlight that sandboxes are at the pod level. We're still discussing the API. Actually, I should mention this whole feature is still in the design phase. But we want to keep it simple. So this is one possible implementation, what the API might look like. So what happens if we have dirty cow and we're running in a sandbox? If you are running Kata containers and your guest kernel is vulnerable, then you can escape the container, but you're still trapped in the VM. You need a hypervisor exploit, some bug in KVM, for instance, to actually get out of there. Similarly, the same is true with gVisor, except it's a different code base, so you wouldn't have dirty cow in the first place. But you might have some other vulnerability. So what's the catch? Why wouldn't you always just run everything in sandboxes and always be safe and secure? This does come with a memory overhead to run that extra kernel, to run the sandbox process. And a bit of performance hit too, especially if you're running in a nested environment. But we're making improvements here. A sandbox isn't going to be 100% compatible with every workload, especially if you need host namespaces or you need to deal with the host network or something. Obviously, if you're sandboxed, you shouldn't be able to do that. Also, if you're running in a sandbox, you don't have the same visibility from the host as you would into a native container process. This isn't because the sandbox is isolated from the host, it's not. But when you're running a native container, processes in the container are just like processes on the host, and it's really easy to kind of introspect in those processes with a lot of the cool monitoring tools that you might be familiar with. And finally, this isn't really a reason not to use sandboxes, but it's not a complete solution. We'll get to that a little later. In particular, it's probably not going to protect your internal network. So now let's move on to talk about attacks via storage. You may have heard about the CVE we announced in Kubernetes a couple months ago. This was a vulnerability in the symlink handling in volumes. So normally when a container reads a symlink in a volume, that symlink is evaluated in the container's mount namespace. This means if that symlink points to etc password, for instance, when the container reads that, it's just going to see the etc password in the container file system, which hopefully isn't too sensitive. However, when you use the subpath feature of the volumes, we mount a subpath from that volume into the container. And when we ask Docker to, or whatever our runtime is, to mount that subpath, it's going to actually follow that symlink and mount the destination. And when it follows that symlink, it follows it in its mount namespace, which happens to be the host mount namespace. And we end up mounting the sensitive file, like the host etc password, for instance, or the Docker socket, or the kubelet credentials into the container. So that's bad. How do sandboxes help us here? Well, one approach to sandboxes, volumes in sandboxes, is to mount the volume on the host and then expose it into the sandbox. So for instance, in Kata containers, one approach is to use the 9P protocol over a VirtIO interface to effectively bind mount the volume into the sandbox. The problem is we're left with the same vulnerability here. When the host goes to mount that volume on its file system, it follows the symlink, we end up mapping that sensitive data into the sandbox, and we see that we only have one single point of failure here. That leads to an exploit. So what can we do about this? This is still design phase, needs more kind of research, but there's a couple ideas of what we can do about it. The first principle is that read-only storage should be exposed via read-only protocols. This means that even if you have a vulnerability that leads to the sandbox process getting at the sandbox kernel, you still can't write to that storage because it's just a read-only device within the sandbox. In the case of ephemeral storage, so the Docker writable layer and empty dir volumes, we should treat those in a way so that they are opaque to the host. For instance, use an image file that represents the whole file system, and then the host never interacts with that data. And this means that any malicious data written there, it's going to be much harder for that to lead to an exploit in the host. We can do a similar thing with block volumes and mount block volumes directly into the sandbox and not onto the host so that, again, they're opaque to the host. And then we have this whole networked file system stuff that's probably the most significant portion of the volumes. And this is kind of a hard problem. One possible solution is we run the client software for those network file systems like NFS, Gluster, Ceph. We run those in the sandbox. And then a vulnerability in that client would just lead to an escape within the sandbox and not into the host. The problem there is we then need to also mount the credentials for that remote storage into the sandbox, and we're effectively moving that security boundary into the remote storage authentication and authorization layer. So it's a bit of a trade-off, and we need to do more research in this area. So let's talk about attacks via the network. Within the cluster, there's a lot of services that are exposed, that aren't exposed to the external world, hopefully. We have various ports on the node. This read-only port that's used in most clusters is unauthenticated and leaks a bunch of data, metadata about the workloads. We're trying to fix that. Metadata service that's exposed by a lot of cloud providers is a common attack vector. If you're mounting service account tokens into your sandbox, then we have to worry about attacks via the API server, any unauthenticated services within the cluster, and also DNS can leak some information. So what can we do about this? Here we're going to look at a different feature other than sandboxes. There's actually a lot of options in this space. A lot of the service meshes can help us here. And network policy can also help. I'm not going to go too deep into this, but this is just an example of a network policy that says, allow all traffic coming out of my sandbox pod except traffic to private IP addresses. And this will vary a little bit depending on your network topology. So now I want to move on to talking about attacks via the different daemons in Kubernetes. Specifically, let's look at attacks via logs. This is sort of a simplified diagram of the log flow on the node. So the logs start from the container. They're written to standard out or standard error. That is a pipe to the runtime, typically, which adds a little bit of metadata to those logs, like the timestamp and which stream it's coming from. Then they're written to the log file. And that log file is read by the kubelet to serve logs requests and eventually gets back to the user. The kubelet just parses the metadata portion of the logs, but eventually that untrusted data is basically flowing from the sandbox all the way to the user. And so the user needs to treat that as untrusted data. Another path is through the logging agent that's running, maybe FluentD, and then pushed out to the log aggregator. Now, FluentD does some parsing and some filtering and maybe some munging of those logs. It depends on your setup. But that means that FluentD is actually looking at that untrusted data and parsing that. So what happens if there's a vulnerability in FluentD triggered by that untrusted log data that leads to code execution? Again, we see there's a single point of failure here. And I was kind of looking back through the history of FluentD vulnerabilities, and I didn't see anything like this as having happened in the past, but that doesn't mean it can't happen in the future. One of the dependencies in FluentD for parsing JSON has had, I saw 7 different bugs with segfault issues. So we can see maybe that could lead to a memory vulnerability. And so what can we do about this? One option is just to sandbox all the things. Sandbox fluentd. So now if you actually do manage to trigger a vulnerability in fluentd, you're still trapped within fluentd's sandbox. And maybe we can use native processes here, or sorry, native containers, because fluentd is our first security boundary, and so a single security boundary might be acceptable there. And finally, I want to talk about attacks via hardware in the wake of Spectre and Meltdown. So Meltdown is a vulnerability where a user space process can read kernel memory. This does not cross a virtualization boundary. So actually, sandboxes do help us in the case of Meltdown. But if we have a sufficiently bad hardware vulnerability, no amount of software isolation is going to save us. And we sort of see this in Spectre variant 2, which does cross the VM boundary. And so if this is within your threat model, kind of the only thing we can do at this point is to just segment those sensitive workloads onto different machines, and then hope that the vulnerability isn't in our network interface, because that would be bad. So in summary, Kubernetes is a very large, complex system with many layers of attack surfaces exposed internally. Sandboxes is an upcoming feature that can help prevent a lot of those internal threat vectors, leveraging hypervisor isolation. And then we're looking at deeper integration into the Kubernetes system to mitigate a lot of threats via these other attack vectors I talked about. The kernel, or I guess that's, the hypervisor isolation gives us kernel isolation, but then there's the storage interfaces, the logging interfaces, and the network interfaces. So when can you use sandboxes? We actually have experimental support today. Both Cryo and Containerd support choosing between different OCI runtimes based on an annotation on the container. And this plugs into the CRI, so you can annotate your pod and take advantage of using Kata and gVisor if you have your cluster set up the right way. This is only protection at the kernel interface, again. I was really hoping to get an alpha out in 1.11. It looks like that's probably not going to happen, so I expect to see an alpha in around 1.12 with an actual Kubernetes API, better implementation via Kata and gVisor, and also some improved resource management that I didn't touch on today. And then as we go to beta, actually looking at hardening a lot of those other interfaces as well. If this sounds cool to you, you can get involved. This first link is to a document on sandboxes that goes into a lot of the challenges with building it, and there's a lot of design discussion happening in the comment section. We're also talking about the design in the sig-node community. And this second link is to where you can find out more about sig-node and our weekly meetings and the different ways to engage there. If you want to contribute code, of course, we're welcoming contributions in sig-node, but also in Kata Containers and gVisor. These are all open source projects looking for external contributions. And that's all I have today. Here's some links to learn more about the different topics I covered. Thank you. And I think we have time for questions.
What about user namespaces and user ID randomization? Do you see this as becoming used in Kubernetes?
Mm-hmm. Yeah, so the question is about user namespaces. User namespaces is a good solution for running as non-root. It's still relying on kernel isolation, so still that single security boundary. There are a few proposals open for how to tie user namespaces into Kubernetes. One of the biggest challenges is around handling permissions of volumes. So if you run, if your pod starts up and mounts a volume and writes some data to it, and then your pod gets killed and restarted elsewhere, maybe it has a different namespace mapping. You end up with different user IDs, and it can no longer read that data from the volume. So we still need to figure out how to deal with that problem. But definitely something we want to add. Any other questions? Can you hand this over?
My question is, would the legacy VMs be able to run in Sandbox without huge modification, or do we expect legacy to be rewritten to run in Sandbox?
Sorry, I didn't catch the first part of the question.
The legacy VMs, will they be able to run in Sandbox? Legacy virtual machines.
Oh, legacy virtual, yeah. Sorry, so the question is about legacy VMs and non-containerized workloads. It's definitely a possibility. Kata Containers is running a VM environment. It is a stripped down VM, so it's not, it might not have the full set of hardware interfaces that your legacy workload needs. It's also a stripped down guest operating system, so we would need a way of specifying the full VM image to the sandbox. There's a project called KubeVirt, which is designed to address this use case, but is currently out of scope for the sandbox feature. Any other questions? All right, I'll be outside if anyone wants to ask more questions privately. Thank you.